Hi, welcome to this short video that shows how to configure a velocity feed-forward system on a TwinCAT NC axis with the Control Techniques drive. Adding velocity feed-forward improves the resolution of the drive's velocity reference by 100 times, which increases performance and decreases motor noise. So for this demonstration, I've got a laptop, and that laptop has been loaded with Control Techniques Connect software, and it's also been loaded with Beckhoff TwinCAT XAE shell. There's an Ethernet connection through to our chosen Beckhoff hardware, which in this case is an IPC, but you'll find the steps are identical whether it's an IPC, controller or PLC from Beckhoff. One of the ports has been configured for EtherCAT comms, and there's a physical connection from that port through to this option module, which is an SI EtherCAT, which is then plugged into a Unidrive M700, making this an EtherCAT axis. Now, if you've got one of our dedicated servo products, such as Digitax HD M753, this interface is built into the product, so right off the bat, that particular drive is already an EtherCAT axis. So, just a quick overview of the control. So, this is a kind of replica of the diagram from the DS402 standard, so that's the standard upon which EtherCAT is based. And you can see here are the CAN objects which are used in our EtherCAT message PDOs. And the standard one that you get is this one, target position 60B0. Okay. Now, in normal control, if you don't do anything to an NC axis, and many other manufacturers PLC open type axes over EtherCAT, you'll find that the target position comes into the target, and then we go and calculate the velocity feed forward reference directly from this position, and we do that by differentiating it. So we're working out the rate of change of this position reference in order to derive the velocity, and then we feed forward that velocity into the control loops. Now that's fine, but when you make this calculation, you're making it based on whole position units instead of parts of position units. So that's where feeding forward the velocity reference, or velocity feed forward reference, gives an improvement. So in this scenario, we enable the velocity feed forward system in CSP modes, that's cyclic synchronous position mode, which is what's used with Beckhoff TwinCAT NC axis. And instead of calculating it by differentiating from the target position, what we do instead is we feed forward directly from the profile generator in the NC axis the velocity feed forward reference and inject it into the control system. How do we do that? Well, we've got a new parameter in the version 2 SI EtherCAT firmware, so it's object OX3000B, okay, subindex 0, and then we set that to a value of 1. So when this index is set to 0, it's the standard mode, so that's the first control scheme that you've seen. If you set it to 1, it's the second scheme where we're able to feed in the external velocity feed forward. Second object that we've got to set up, and this is a PDO mapping now instead of a startup list item, is object OX60B1. Okay, and this is where we actually inject the final reference that we're going to calculate. So before we get into the demonstration, I just want to point out that all of the steps in this video, and all of the other ones in fact in this series of videos for TwinCAT, is covered in depth with step-by-step instructions in this user guide. So if I show you, if I expand how-to guides and then come down here, you can see how to apply velocity feed forward to an NC axis. This diagram should be familiar, we've looked at it just before, so all of the steps that we're going to cover in this video are also covered step by step by this document. So let's get into it. So to start off with, I've got a program that I've already written. I'll just cover briefly what's inside of it so it's not too much of a mystery. So we've made a brand new project. I've told the project about our IPC target. I've then scanned the network for masters, so it now knows about our EtherCAT master. I then scanned for boxes, found our drive, okay, so our EtherCAT slave, and when it found that, it asked me, did I want to add an NC axis or a CNC axis? I chose to add an NC axis, so I added this axis to the pool. I've then since scaled it up so it knows what my conversion between units is, so in this case I've got 1000 units per 1 rev at 16-bit resolution. And then I've gone and set up all of the normal limits. I've set the maximum speed and things like that. Okay, then in my program, I've added an instance of axis ref, which is just what you have to do for PLC open axes, of which NC axis is one. And then rather than adding in MC move velocity, MC halt, MC power and all of those things, I've included this block which uses those under the hood, which is from the Control Techniques NC CT axis interface library. It just makes it easier for me to just apply a basic speed reference in order to be able to see the effect of the velocity feed forward working. Okay, so what I'm going to do now is I'm going to cause the axis to run. Okay, so I'm going to do drive on, which is effectively the equivalent of MC power, and then I'm going to ask it to jog. And there we go, my axis is now running. So if I transfer back to the view in Control Techniques Connect, what we can see is that we've got a speed reference coming out in the order of 58 RPM. Okay. Second thing that you can see is that this external position reference scheme, so what we're actually looking at here is the motion controller that's built into the product. And what we can see is that the external position reference and speed reference are both inactive. Okay, they're not selected. So that's telling us that we haven't engaged the velocity feed forward. So this will become important later. So once we've actually engaged the velocity feed forward, if we want to see that it's actually working, we can come back and make sure that these external reference values are being updated. So let's get back to the code. So I'm just going to stop my axis now. And there we go, my drive's disabled. So I'm going to log out and then we can begin to go and add the extra pieces that we need. So the first thing that we need for an NC axis anyway, NC axis, if you map up the PDO in order to transfer the velocity feed forward reference, unlike a CNC axis, where this step is kind of done for you, unfortunately in an NC axis it doesn't have the ability natively to do velocity feed forward. So if you want to do it, you have to manually calculate it, and it's only 2 lines of code, so it's not too onerous. So if you want that extra performance, you basically have to put in 2 extra lines of code. So that's what we're going to do now. So what I'm going to do is I'm going to make a variable that will hold our velocity feed forward reference. So here we go. I think that will do. And then what I'm going to do is I'm going to place this variable in the PLC registers, I, Q and M registers. So in this case, velocity feed forward is an output, therefore it needs to go into Q registers. So to do that, you use this extra command @ and then it'll be %Q*. The asterisk means that it goes and places it in memory wherever the system thinks it would be appropriate. You don't actually need to know where that goes, it's kind of not relevant, the system will just sort it out. So that's the best way to achieve that. And then it needs to be of type dint, and that's because all of the interfacing parameters that go into the DS402 interface, which is where the velocity feed forward reference goes to, are all of type dint. Okay, that's as much as we need. So next thing, after our motion has been called, so just to clarify, we've got our main task, and then I've got an action that gets called from our main, and then our main motion, as you saw before. Come on. Not sure why that's not working. Just because I've got 2. There we go. Our main motion is caused inside of this action. So what you need to have happen is your motion commands need to have been executed, and then you need to read the velocity from your motion interface, from our axis ref. So that's what we're going to do now. So I'm going to call our velocity feed forward. So we're doing this after our motion has been called, and we're going to go and set this. So what we need to do is we need to say axis 1, because we're going to read the speed from our axis. It's NC to PLC, and then we're looking for set velocity. There we go, set velo. Okay, so Next thing that we need to do is we need to scale that. So at the moment, that velocity will be in user units per second, but what we actually want that in is encoder counts per second. So we need to use our scaling ratio, and you get that scaling ratio from your encoder object. So if I click on here and then go parameter, we can see that our scaling factor is 1000 user units per revolution over 65536 counts per revolution. Okay, so it's 1000 and 65536 are our scaling factors. So if I come back to main, we are converting from units to encoder counts. So we multiply by the number of encoder counts per rev, and then we divide by the number of units per rev. And there we go. And the last thing that I need to do is I need to convert this, because at the moment this is all L-real, and as I mentioned before, this is a DINT. So we need to do the standard conversion. So we need to go L-real to DINT, and there we go. So that's everything. So the next thing that we need to do is we need to build this. So I'm going to do it visually, build solution. And the reason that we are building this at this point is because we need this velocity feed forward reference to become a selectable object when we go and set up our PDO mappings. Okay, if you haven't built successfully, this variable won't be selectable as something that you can link to in the PDO mappings. Okay, so next thing we have to go and sort out our startup list. Okay, so we need to go and enable the feature. So let's go and do that. So if I double click on our axis, there we go, and then startup, and then I'm going to just make myself a little bit more room here. There we go. If I go new, because we're going to go and add a new item, and then we can scroll down this list and we should find 3000 and B. There we go, enable velocity feed forward, because that's the function that we're doing. And all we need to do is we need to change this right 0 to a 1. Okay, and then that will become enabled, and we click OK, and there we go. You can see that it's been set to a 1. So next thing that we need to do, we need to go and set up our PDO mapping. So we've enabled the feature. Now what we need to do is hook in that variable that we calculated before, so that we can pass it into the drive so that it can become the velocity feed forward. So let's go and do that. So we need to click the process data tab, and we need this one. There we go, control word and target position. So it's OX1602. So these are the outgoing objects in CSP mode, cyclic synchronous position, and we're going to go and add something to it, our velocity feed forward. So I'm going to select an empty space, right click and go add new item. Now so we just got to scan down this list. There we go, for velocity offset. So you know, if you're in some of the other modes, this is used as a velocity offset. In CSP it's used as velocity feed forward, so don't be confused by that. So select object 60B1 from the list and then click OK. So if we go and take a look, we can now see that it's there as an output. Okay, but at the moment it's not linked to our data because we've had to manually calculate that. It doesn't automatically link in. So what we need to do is double click velocity offset from this list, and then this opens up the link picker. Okay, now if you remember, when we set up this variable, we did @%q asterisk, and what that meant is it put it in memory, in PLC register memory, which is a place where this link picker knows about. Okay, so you can see there's our variable. We click OK, and now that's mapped, and you can see that it's mapped because now it's got this little box with an arrow in it telling us that it's all linked up. And that's everything that you need to do. So let's go and run our code. So I'm going to go log in with download. So that's going to push the code into the target. And actually, I think I need to apply that as well because it's a change to things in the tree. there we go. I think that should be working now. So I'm just going to log back in again. There we go. So now I'm going to do exactly the same thing that I did before. I'm just going to ask my Axis to run. So I'm going to enable the drive, and then I'm going to give it a run. And I can see that my Axis is running. So let's now go back. What you can see now is that our external position reference is updating. We can see that our external reference select is enabled, and we can see our speed reference is coming through. Now, if you note, before our speed reference was something like, I think it was sort of 58 RPM. What you can see now, because we've got another 2 decimal places of accuracy here, actually, and this is normal, it's sort of just dithering around 60 RPM, which is exactly what the speed should be. So you can see that by enabling the velocity feed forward, the granularity of your velocity reference is much, much smaller, 100 times. And that's worth having, okay? So I hope you found this useful. Thanks for watching.